Ladies and gentlemen, welcome to our webinar. Today we gather here to explore the remarkable convergence of the innovation and sustainability, where cutting-edge technology is poised to redefine the very core of energy storage. At the heart of this transformation stands a remarkable material, the single-wall carbon nanotubes, or short single-wall CNTs, and its extraordinary potential to revolutionize the battery technology. So from my side, again, a very warm welcome for everybody joining this webinar today. My name is Joshua Franzke, and I'm the Business Development Manager at OCSiAl for our battery grades in Europe. And I'm here today together with my colleague, Andrej Seniut, the Senior Vice President of OCSiAl Product Development Team. And Andrej has already worked for 10 years in the battery industry, driving innovation forward with our single-wall CNTs technology, and is responsible for our global battery technology roadmap. So together we will delve into the incredible ways in which TUBALL is being harnessed to enhance the performance, safety, and of course also the sustainability of the batteries, from extending the battery life, increasing the energy density, and improving conductivity. The potential applications of the single-wall CNTs in batteries are nothing short of revolutionary. So the presentation will last approximately 25 minutes, after which we will have a 15-minute Q&A session. And to ask any questions, you only need to click at the bottom on the lower side on your screen and type your question in the chat. You can do so at any time during the webinar. And in the Q&A session, we will then try to answer as many questions as possible. And of course, if we do not answer your questions in the Q&A session, we will come back to you by the email that you can also send your questions to webinar@oxial.com. And in case you missed anything or want to rewatch the webinar, it will of course also be recorded. So fasten your seatbelts as we embark on an electrifying journey into the remarkable world of the single-wall CNTs and their profound impact on batteries and innovation that promises to redefine
products for lithium-ion battery industry based on single-wall carbon nanotubes for already about 10 years. And we gained a lot of experience both from academia and the industry about the performance of our material. And this is the purpose of today's webinar, to share with you the most up-to-date information about potential and existing applications of single-wall carbon nanotubes in the field of batteries. But before I'll do so, I'll start with explanation of the mechanisms behind single-wall carbon nanotube work in lithium-ion batteries. I will start with single-wall carbon nanotube properties. And if I were to summarize why single-wall carbon nanotubes in the batteries work in a different manner and outperform competing conductive additives such as carbon black and multiwall carbon nanotubes, I would summarize this in one sentence. So single-wall carbon nanotubes, this is nature's longest and most flexible material for conductivity and reinforcement of electrodes. So this simple sentence actually describes a lot about how single-wall carbon nanotubes work in the batteries, to which I'll jump a little bit later. But now, to prove the statement, please look at these TEM images of different conductive materials which can be used as a conductive and reinforcing additives in lithium-ion batteries. And as you can see to the left side, the single-wall carbon nanotubes, and only by looking at the images, you can see that this material is substantially longer and flexible in comparison with carbon black and multiwall carbon nanotubes. So this difference in morphology of single-wall carbon nanotubes actually determines the difference in performance of our material in various battery systems. Why? Because carbon black and multiwall carbon nanotubes, this is the material which is small in size and quite rigid. The material more covers the surface of active material particles, which you can see here to the left on this slide. And these surface connections create some sort of residential roads for electrodes, which promote short distance conductivity. This is good for charge transfer from electrolyte, but requires more conductive material inside to establish connections between the particles, as well leads to higher bulk electrode resistance, and these connections are not stable. At the same time, Single carbon nanotubes create long-distance connections and bonds between the particles of active material. And these bonds act like some sort of high-speed highways between active material particles, which are highly conductive, highly strong. And thus, these connections allow to conduct high currents and as well as stable, even, for example, when there is a severe volume expansion and contraction of your battery active material. So this mechanism, this difference in the working mechanisms of single carbon nanotubes versus multiple carbon nanotubes and carbon black determine the areas of application of single carbon nanotubes where this unique morphology of single carbon nanotubes play essential role. And over these 10 years of working with customers, like supporting customer tests, doing our own research, we've been able to identify, as of today, 3 commercial applications in the field of lithium-ion batteries where single carbon nanotubes substantially outperform competing conductive materials and are essential to be used. One of the applications, and perhaps if you're familiar with our product, you know really well, this is silicon-based anodes. This is a system with very high volume expansion and contraction. And here, these like long and flexible single carbon nanotubes, which are able to establish reliable connections between silicon anode particles, are very useful. Second application, which we found out recently, this is thicker electrodes. And the mechanism of the work is actually the same. The thicker you go in the thickness of your electrode, first of all, the more non-uniform is your conductivity. If you speak about application of classical conductive additives such as carbon black and multiple carbon nanotubes, due to many reasons. For example, due to the reason that during the drying process, because they are small, they tend to go up towards the electrode surface. And this is why throughout the thickness of the electrode, the conductivity is not uniform. And second, just imagine like thick electrode is similar to thick layer of paint on the substrate. If the layer is too thick, it starts to crack. And here it turned out that application of single carbon nanotubes allow to improve both mechanical characteristics of the electrodes and as well assure uniform electrical conductivity throughout all the thickness of the electrode. And obviously last application about which I will speak today, this is high performance cathodes and anodes. So this is the application which require just to max out everything from your cathode and anode. And the most conductive, the most like durable, conductive and reinforcing materials such as single carbon nanotubes allow to do that, allow to achieve high discharge rates, allow to lower DCR, allow to use the record low dosage of single carbon nanotubes to assure the required battery resistance, etc. I'll show you a little bit more details about these applications over the course of my presentation. So let's start about silicon-containing anodes. And to start with, I'll show you a very brief illustrative video about how single carbon nanotubes work inside silicon anode battery. So the mechanism is really simple. Now you can see a crosscut of the cylindrical battery. So to the left, this is the anode side. To the right, this is cathode. And these yellow dots, this is lithium ions. These black particles, this is the particles of silicon anode material. And as you can see, during charging process, silicon anode particles enlarge. During discharging process, now it's a charging process, they contract. And over this course of expansion and contraction, there is a loss of electrical contact between silicon anode particles, which leads to rapid battery degradation. And single carbon nanotubes, this is real scanning electron microscope pictures of silicon anodes, allow to create these bridges between silicon anode particles at a very long distance and assure that even when there is a very high volumetric expansion in your anode and contraction, the particles stay electrically connected, and thus the cycle life improves substantially. So this is one of the most typical results in silicon-containing anodes. In this case, I present you cylindrical battery 18650 with 10% of silicon oxide inside. but actually it's not that important about which silicon material are we speaking. Silicon carbon, like even metallurgical silicon, it doesn't matter because the principle is the same. Carbon nanotubes allow to create established connections between silicon anode particles in a very reliable manner. So the cycle life is improved substantially. In this case, only 0.05% of TUBALL, this is a trademark of our product, allowed to improve the cycle life like almost twice and reach the cycle life equal to 1,000 cycles, whereas multi-wall carbon nanotubes, 1%, so 20 times higher dosage, allowed to reach the cycle life equal to only 550 cycles. But what's very important and like essential to understand the areas of application of single carbon nanotubes is that the more silicon is in the battery, the more pronounced is the effect. In this case, this is 90% silicon oxide battery. And in this kind of system, multiple carbon nanotubes do not work at all. And the same goes valid if we speak about few wall carbon nanotubes, if we speak about some like less flexible, less long structures. Whereas single carbon nanotubes continue to work. In this case, it was also 0.05% of TUBALL, which was used as an additive in the battery, versus 3% of multiple carbon nanotubes. Yes, the overall cycle life is smaller, but this is 90% silicon oxide and lab tests. But you can see the difference in the performance, which can be applied and translated if you're developing your own battery with a silicon-rich anode, 30%, 40%, etc. So now let's speak about cathodes. The working principle is the same. Single carbon nanotubes allow to create robust long-distance electrical connections between the particles. In this case, this is the scanning electron microscope image of NCM811. These networks looks something like this. I hope you're able to see the video. So they both span through over the surface of the particles and between the particles. In this case, they're animated with this blue like, flowing current. And these networks which connect particles together allow to improve key battery performance characteristics, such as higher energy density, better safety, higher discharge power, better adhesion, or it's more correct to say cohesion between the particles. Overall battery DCR is reduced. Overall battery cycle life can be improved. Also, as a side effect, sometimes customers see the better effect on thermal stability of the battery because the battery basically doesn't generate as much heat as if we speak about the batteries with conventional conductive additives because the overall battery resistance is higher. So this is just to summarize what I just said. So higher battery safety due to lower battery internals resistance, high energy density because the loading of single carbon nanotubes is from 10 to 60 times lower in comparison with carbon black and multiple carbon nanotubes. This is why you can put more active material inside the battery to achieve high energy density. Third one, this is higher discharge power. Typically, this is observed at very high discharge rates, higher than 3C, 4C, 5C, where already conductive network plays the role in such kind of performance. And the last one, this is improved cohesion between the particles. Because these networks of single carbon nanotubes, they are long distance and more interparticle, contrary to multiple carbon nanotubes and carbon black. So just some results to illustrate what I have just said. So lower dosage, from 10 to 60 times lower, but I like another interpretation of this result is that 3 or 4 kgs of conductive carbon black in EV battery pack can be replaced with only 100 grams of TUBALL to achieve the same level of, in this case, electrode resistance on PET film. Lower DCR, so to the left, this is the control group with multiple carbon nanotubes 0.4 plus 0.8 carbon black. And first of all, in comparison with groups which are to the right, 0.05 TUBALL plus 1% of Super P. So what you can see, so first of all, initial DCR was lower, 65 milliohms versus 58 milliohm in groups with TUBALL. And also the DCR growth was slower with single carbon nanotubes in the recipe of the battery. So DCR grew in multiple carbon nanotube group to 95 milliohm, whereas with single carbon nanotubes to 67 milliohm. This is quite fresh results, but very exciting, and these results lead to traction on the market. We see more and more projects now applying single carbon nanotubes in these kind of systems. I'm speaking about thicker cathodes and anodes. So because single carbon nanotubes improve the cohesion between the particles, between active material particles, the mechanical strength and flexibility of the electrode is improved. In this case, this is a comparison of graphite anode, standard 12 milligram per square centimeter one-side loading, 96% graphite, 1.2% CMC, 1% carbon black, 1.8% SBR. And you can see that by testing this anode by using 5mm band, there is a crack in the anode. But if you add only 0.1% of TUBALL on top, you can increase the loading of your electrode up to 20 milligram per square centimeter. And by doing the same test, you do not see cracks. So the electrode is more flexible, it bends more well. If you add more TUBALL, the result is even more pronounced. So plus 0.3 TUBALL on top, you can increase the loading higher than 25% milligram per square centimeter one side. And the same if we speak about cathodes. In this case, this is the result in LFP cathodes. We tried to maximize the thickness of the cathode one-side loading till the stage when we started to observe cracks on the surface of the electrode. To the left, this is carbon black group. In the middle, this is multiple carbon nanotubes group. And to the right, this is TUBALL group. So with Super P, we started to observe cracks at about 18 milligram per square centimeter one-side loading. With multiple carbon nanotubes, we started to observe cracks at 32 milligram per square centimeter loading. With TUBALL 45 plus milligrams per square centimeter, no cracks. Obviously, this result might be not directly applicable for EV recipes, even though we have customers who are trying to maximize the thickness of the electrodes, the loading of the electrodes to 40 milligram per square centimeter one side. But this can be easily applied to ESS applications, because in this case, your battery doesn't need to charge and discharge that fast, but energy density and economy is crucial. And the thicker are your electrodes, the better is the ratio of active material to inactive, the better is energy density parameters, and as well, the better are the cost parameters. So this is what I really recommend you to check in your laboratories if you are developing batteries with thicker electrodes. Our material can be quite useful for such kind of applications. In terms of areas of application of single carbon nanotubes, dry electrodes obviously is the direction where we are going. Here we think that our material can become even more essential, because typically the distribution of conductive additives on the surface of dry electrodes is not that good. But if you introduce very long, very flexible structures inside dry electrode, it's more easy to assure very good cohesion between them and assure the uniformity of conductive network. We're already doing these tests like in our laboratories, in partner laboratories. We have already the proof of concept samples of the concentrates made of TUBALL and PTFE. In case you are interested in this kind of application, please send us your inquiries. You can send them via webinar@ocsal.com email, or just approach us via some other method. But this is like the next development direction, next generation development direction, which we are heavily pursuing. Just to show you the proof of concept result which we have achieved in our laboratory. So this is a freestanding dry cathode, NCM811, with about 1% of PTFE and with single carbon nanotubes inside, with a very high thickness. So as you can see, this electrode is quite flexible, it's quite durable, and we tested its basic electrochemicals performance, and obviously the electrochemical performance of other recipes which we are developing. the cathodes work pretty well. And now we are developing solutions for anodes, where we're trying to use different approaches, for example, coating of active material with TUBALL to the surface, or creating concentrates for the anode applications as well. So I will end my presentation with information about the products we have in the company. So for lithium-ion battery market, we're offering currently different kinds of dispersions, both for anodes and for cathodes. So for anodes, obviously dispersion in water with different dosages and different binders inside, mostly CMC. For cathodes, obviously dispersion in NMP. So this is how our product line as of today looks like. So today we are offering 0.4, 1%, 0.4 dispersion in terms of concentration of TUBALL for the cathodes. First two dispersions contain PVDF as a thickener, and the last one contains HNBR, like a dispersing agent to achieve more fine TUBALL dispersion in NMP. For water-based, for anodes, we are offering water-based dispersion, 0.4 TUBALL, 0.6 CMC, 0.8 TUBALL, 0.8 CMC. The dispersions with higher TUBALL concentrations, so 1% TUBALL BAT NMP and 0.8% TUBALL BAT H2O. These are our most fresh products, which we launched to the market basically end of last year, this year. We're aiming to produce these dispersions in Europe. For water-based dispersion, we're already building a plant in Serbia with a production capacity equal to 3,500 tons per year of water-based dispersion, which will be launched closer to May, June 2024. For NMP-based dispersions, we as well will have European manufacturing of NMP-based dispersions. We are now at the stage of site selection, speaking with different partners, trying to find the most suitable location where we will build our own manufacturing of NMP-based dispersion for cathodes. So summarizing about us as a company. So OCSiAl today is the world's largest producer of single carbon nanotubes and the only company with a scaled and scalable technology of synthesis of single carbon nanotubes. This is a revolutionary material which has applications beyond batteries. We see and estimate that more than 50% of the materials around us can be improved with single carbon nanotubes. We have a patented technology with more than 100 patents and patent applications in 40 countries. The material is in mass production, and we will have capacity up to 120 tons per year of single carbon nanotubes in 2026. And have global R&D in different countries. And if we summarize the volume of the material which can be enhanced in lithium-ion battery industry, if our material is used only in batteries, today in 2026 we have production capacity enough for more than 200 gigawatt hours of lithium-ion batteries. So this is some information about the plant in Serbia, which we are building right now. So the plant will be located in Stara Pazova, the city close to Belgrade, which will employ around 200 employees, 8,000 square meters. So this is the picture of our building, which we have. We'll produce both concentrates for other applications, non-battery applications, and dispersions, together with synthesis of single carbon nanotubes. So we'll have production capacity of 200 tons per year of concentrates for non-battery applications, 3,500 tons of dispersion production capacity for battery applications, and 120 tons of single carbon nanotube production in Serbia. In terms of our R&D capabilities, so we have 3 R&D centers currently in Luxembourg, in Belgrade, and in Shanghai, which can do different advanced tests in the field of lithium-ion batteries. We have like a pilot line in Shanghai TUBALL center able to work with the most advanced battery materials, NCM811, NCA, silicon oxide, etc. So we're encouraging you to collaborate with us. In case you have some special requests, please feel free to contact us. And I am ending my presentation, and we are ready for Q&A session. I saw there are some questions in the chat.
Perfect. Thank you very much, Andrej. So thank you very much for the presentation. So indeed, we have quite a few questions already. So let's start. The Q&A session will last for approximately 15 minutes. So we have quite a bit of time to address the individual questions here. So let me pick the very first one, which is, what about, from Mr. Bansal, what about the cost of the overall anode active material? How does that change compared to normal carbon additive, and how does it affect the dollar per kilowatt hour of the battery?
Joshua, will you address this, or should I address this question?
So feel free to add your comments here, and then I will follow up.
Yeah. So if we take our existing today's prices, both for single carbon nanotubes and for the dispersion, then if our material is applied on the anode side, we are less than 0.5% of the total bill of material if we speak about cost per kilowatt hour. So less than like 1 or even smaller than 0.5% of dollars per kilowatt hour of the battery. So this is like the cost of application of our product.
Yeah, so basically you can substitute, as it was mentioned during the webinar, you can substitute quite a lot of different carbon black or the multiwall CNTs inside of your electrode slurry. So the TUBALL itself is at the moment a little bit more expensive than the multiwall CNTs and the carbon black, of course. But while you can then reduce the content of the other carbon additives, then it balances it out and can be, even as Andrej said, cheaper in terms of kilowatt hour. So then we have from Jean-Luc Vincent the question regarding LFP using CNTs. Which side, anode or cathode, is best to improve with the single wall CNTs or CNTs to be added? Andrej?
So it really depends on your system. If you are developing LFP plus silicon anode, it's very difficult to answer these questions because like anode will be improved substantially and thicker LFP as well. So I would say if this is a more standard recipe such as LFP graphite batteries, then it's like the more benefits will arrive from applying of TUBALL on the cathode side if you are developing thicker electrodes. But once again, if this is like LFP silicon battery, or this is LFP fast charging graphite battery, then both sides would be improved. And obviously we have different guidelines, etc. Now I'm answering quite briefly, but we have all these guidelines, recommendations, test results. So please feel free to share with us the questions. More questions, we'll be able to support you with different kind of data later on.
Perfect, thank you. Then from Payam Hashemi, we have the question, why TUBALL single wall CNT dispersion for anode and cathode have very low concentration but high viscosity? Do they already contain the binder for whole formulation? And is the concentration a technical limitation?
So thank you for your question. The high viscosity comes not from the binder. Even though our dispersions contain some amount of binder or dispersing agent, but this is not the whole amount which you need to develop your anode recipe or cathode recipe. High viscosity comes from the morphology of single carbon nanotubes or the aspect ratio. So this is very long, very long material with high surface area, which generate the viscosity. And there are a lot of trillions of the particles of single carbon nanotubes in the dispersion. So if you disperse them well, you will have like very substantial amount of the particles with high surface area in your anode, in water or in NMP, and this creates the viscosity. At the same time, I would like to address your concern that like the amount of nanotubes is low. With 0.4, 0.8 concentration of single carbon nanotubes on the in water-based dispersion or in NMP-based dispersion, it's possible to achieve very high solids because the dosage of single carbon nanotubes in the electrodes is very low, typically around 0.05%. So on the cathode side, It's easy to achieve 80% solid content with 1% NMP dispersion. On the anode side, 50-55% plus with highly concentrated dispersions. So basically, we already optimized the concentration of nanotubes in our dispersion in order for it to be used in a quite user-friendly manner by our customers.
Thank you. Then we have actually also quite a few questions regarding the dry coating. So starting with Ronald Gordon regarding the dry coating, since the SWCNTs comes as a dispersion, NMP or water-based, how do you incorporate this material in a dry coating process, specifically during dry mixing of the initial powders?
So obviously, dry mixing technology is like in development, so different customers using different approaches. But we use a quite conventional method of introduction of single carbon nanotubes into dry electrodes. But first of all, we start with a TUBALL, PTFE, or TUBALL plus some other material concentrates. So we pre-mix TUBALL with slight dosage of PTFE, or pre-mix TUBALL in a different carrier medias in order for single carbon nanotubes to be like at least slightly dispersed and be non-dusty. And then you can use standard Irich mixer or jet mill. You add your active materials, you add the missing amount of PTFE, you add this TUBALL PTFE concentrate, the mixing is done, and then you can use quite standard calendars which are applied in the industry in dry mixing, like Sauerzik presses, etc., etc. So in the lab, we have even more simple setup. You can use some sort of pasta machine to like roll multiple types your dry electrodes in order to show the mixing of your active material. But this is for like small proof of concept test. This approach can be used. We would be happy to give you more details or like after our presentation, after our webinar about this application.
Perfect. Well, then you answered already to some degree the question from Vladislav Borshkov. What kind of mixture are you working on for the DBE? That you already answered. So the follow-up question here is, what are your proposals to modify the current convenient consequence of dry electrode production?
I do not get, frankly speaking, the second part of the question. So Vladislav, if you would be able to address these questions to us later on about what do you mean by current convenient consequence of dry electrode mixing, we'd be happy to discuss this matter and give you more explicit answer.
Yeah, so you can send again then the question, of course, also to webinar@oxial.com, and there we will also reply to you directly to your question or to the questions which we are not answering right now during the Q&A session. So then the next question is from Chengyang Pan. Does the CNT only improve the cohesion of the particles, or it also improves adhesion to the foils at the current collectors?
I would say yes, CNT improves the cohesion between the particles, but if you want to improve the adhesion to current collector, you can coat a very thin layer of single carbon nanotubes on the surface of your current collector. And this approach really works really well, works better than carbon-coated foil because the thickness of this coating would be smaller, lower in comparison with coating with carbon black or with multiple carbon nanotubes due to just the size of single carbon nanotubes. At one point of time, we had a product in our portfolio like this, but it was quite difficult for us to go into mass production of this single carbon nanotubes coated foils. So this is why now we are giving recommendations to the customers in case customers are willing to improve the adhesion to the foil. And by the way, for dry mixing, especially for the anode side, we highly recommend to prime your copper current collector with single carbon nanotubes because this allows to assure more stable battery performance. We saw it in our laboratories, and actually this approach works really well.
Then we have one other question from Matthew Capener. How stable are the SWCNT dispersions over time? Is any remixing required?
They're stable. Shelf life of water-based dispersion is 1 year. very stable, no remixing is required. But if you are using big IBC tanks, if you're using very high in solid content single carbon nanotube dispersion, such as 0.8%, then we would recommend to just steer our dispersion IBC tanks in order to assure better pumping. But overall, this is just a general recommendation. You can use our dispersions as is without needing to steer them over the course of the storage. For an MP, it's 6 months, but we will extend the shelf life to 1 year and over the course of like next year, because they are as well stable in terms of the dispersion itself. The issue with an MP dispersion that an MP grabs moisture from there. So this is why we set the shelf life for an MP dispersion equal to 6 months, just to assure that we have a very low moisture content in ppm in our dispersions.
Perfect. We have also one question from Naid Kaiser. Is it possible to tune the amount of binder additive in the single-wall CNT solution? And if yes, how can it impact the electrochemical performance? So to answer your first question, Nahid, we can discuss, of course, always in a direct case together to see what sort of options we would have available to produce for you. At the end, the portfolio that we've shown earlier in the webinar, this is the portfolio what is commercially available, and any other developments we can discuss, of course, always direct together, especially also for your cell chemistry. And regarding the second part of the question, how can it impact the electrochemical performance? What sort of binder or additive is being used in the CNT solution? Andrej, I leave it to you.
Oh, it depends really on the binder and on the changes. Yes, so it's very difficult to answer without specifics. But sometimes just I'll answer in a little bit other direction. For example, what we see in dry electrode, in dry battery electrode systems, that you can, because single carbon nanotubes themselves act like a binder, conductive binder, I would say. They improve the cohesion between the particles. You can actually reduce the amount of the binder in your electrode. So in some cases, the positive effect of applying single carbon nanotubes and changing the binder ratio could be in the fact that you could use a little bit less binder in your system. But if you speak about reducing the amount of dispersing agents in our dispersion, it can have a negative effect on the dispersion quality of single carbon nanotubes. So we need to discuss in more specifics. So what is your idea, whether we can fulfill your needs in a tailored manner.
Perfect. Then we have also one final question, or we maybe just pick one other question then as well, because we are reaching towards the end of the Q&A session. From Yihui, is it a good practice to use both single-wall CNT and Super P in the electrodes, or just simply use the single-wall CNTs themselves?
Depends on the electrode. On the cathode side, I would say that your question is very accurate and provides the answer. Typically, we recommend to combine Super P with single carbon nanotubes. Why? Because of the different mechanisms of how these two materials create conductive network inside the electrode. Super P more covers the surface, better for charge transfer in the electrode, better to achieve a little bit higher electrolyte absorption in your electrode. Single carbon nanotubes to create very long distance interparticle connections, which can conduct very, very high currents. So on the cathode side, I would recommend to combine with Super P. On the anode side, in silicon, basically there is no need for such combination. In fast charging graphite as well, because graphite is conductive itself. Silicon containing anodes, basically it's sufficient based on our experience to use only single carbon nanotubes in this system. Very general recommendation. Obviously, we can discuss specifics later.
Of course. So we are reaching 11:40. The Q&A session is hereby ending. Of course, the questions which Andrej and myself did not answer in this Q&A will be answered later on by email. So feel free to again mention your questions to webinar@oxial.com. We will then answer your questions in the due course. And of course, I see also quite a few familiar faces. If you have any questions after the webinar, please feel also free to send me and Andrej also direct emails, and also give us a call. We are available anytime for you. And from my side, Andrej, thank you very much for the very nice and interesting presentation, and very good answers to the Q&A. So from my side, again, thank you very much for everybody joining, and I hope you have a wonderful day or afternoon or evening, depending on where you are.
Thank you, Joshua, for your support. Thank you, colleagues, partners, friends, for coming. Enjoy the day, the night here, depends wherever you are. Thank you.
Thank you.